So my name is Atsushi Suzuki, and today I'll talk about quadruple arithmetic computation for FreeFEM to simulate a semiconductor problem. So I think it's better to off my video because my network is slow. So yesterday Frederick introduced me as a kind of developing of quadruple precision arithmetic in FreeFM. But unfortunately, today total my project is not yet finished. But now I have some results by real computation by quadruple arithmetic. But I am talking about in the future what we can do. So first, I will review a semiconductor problem, which is solved by mixed formulation, but it requires quadruple precision because very high condition number in the case of the problem, which consists of NPN device. And the finite element matrix should be generated by quadruple precision. And also the solution by linear system is in quadruple precision. But it could be done by dissection sparse solver. And then the problem of NPN device is very difficult. This is very academic problem, but actually that's difficult because there are kind of pseudo kernels in the problem. So on the last, I'd like to overview the project to work with quadruple precision in FreeFM script. First, I would like to start a physical system of the semiconductor problem. Three unknowns. One is electrostatic potential. Next one is electron concentration. The third one is hole concentration. There are three equations. All unknowns is scaled by Demari scaling, and then that is dimensionless. So we need to solve the three equations. The difficulty comes from the nonlinearity embedded in drift term. Drift term is Jn is expressed with gradient n minus n gradient phi. To resolve this one, usually we do introduce so-called slot-room variables. So with exponential weight of electrostatic potential. So by setting n equal exponential phi times eta, the system of the drift term becomes simpler. Just E phi exponential phi times grad eta, or exponential minus phi times grad xi. So the system becomes kind of the diffusion type system. But difficulty is the weight of exponential is something that it has huge magnitude. So it causes bring us very high condition number. But at the first, I briefly review of the schematic of NPN device. So there are two different kinds of the semiconductor. One is enriched region, and the other one is p-rich region. Enriched region means there are a lot of electrons in there, and p-rich region is there are a lot of the hole in there. And then on these each regions, there is kind of the substance exists during the manufacturing process. And then we need to put boundary conditions. The boundary conditions consists of two different one. Is simple one, just the Dirichlet or Neumann. For boundary 2 and then 4, we put the Dirichlet boundary condition, which satisfies so-called thermal equilibrium. On the thermal equilibrium, product of n and p non-dimensionalized values is equal to 1. And then little bit calculation, we could get appropriate value to satisfy the thermal equilibrium for electrostatic potential. But anyway, this is kind of the Dirichlet boundary, inhomogeneous Dirichlet boundary data. And then below and then top boundaries 1 and 3, we put a Neumann zero boundary condition there. So we'd like to solve the diffusion system with this kind of the boundary conditions. And then in practical, we put kind of the bias to the left wall. It's called as phi up. Is the real value is 0.01, but after dimensionless scaling, this value becomes 0.38. So this value is not too small, but it has some kind of significant effect to the solution. we would like to see that later. So the system we need to solve consists of kind of the mixed type formulation, because we need to deal with density of electron or hole, and then plus its gradient. So we introduce kind of the weak formulation of using the H divergence space. This is slightly similar to reservoir problem, where the conservative law is very essential. In this case, I use the same methodology. And the system is nonlinear, so we need to solve this system by Newton iteration. To do that, first I will calculate fresh derivative of this system. So linearized system consists of these three lines with given phi, jn, eta, jp, and xi. We need to find delta phi, delta jn, delta eta, delta jp, delta xi. So of course, this is a variational formulation. In the FreeFEM, we can write almost directly these equations by script. But in real computation, sometimes we would like to refer a matrix form. So by writing of the matrix form, it is easy to see the character of the matrix. It's contained of the two kinds of the block of KKT type, Stokes type blocks, M and B transpose, minus B and 0. So this is very similar to the Stokes style because of the mixed formulation. And then I have to think about where is nonlinearity. Nonlinearity comes from A phi or C phi or DJN, DJP. Diagonal of A, and then other one comes from the off diagonal. And also M contains weight of the previous phi k. But this is linearized. So we need to solve the linear system for electron or hole using the previous value of the electrostatic potential. So this is a system. And then at the most simplest case, we need to solve linearized mixed formulation for whole unknowns of the gradient and then value itself. It consists of this kind of the weak formulation. Phi k is given. So first term with exponential is weight, and then Jp dot V is L2 inner product of H dive space. Next one is gradient divergence condition, and then kind of the Lagrangian form, Lagrangian multiplier. So if we want to write this kind of equation in FreeFEM script, it is not more difficult. Nothing difficult. Just define F space BH on the TH mesh, and then Labiatoma lowest order element. Next one is for whole concentration. Space name is QH, and then on the mesh, same mesh on TH, and the P1 element. And then for electrostatic previous value of the electrostatic potential, I use XH function based on the same mesh and with P1 element. And then by definition of variational formulation on L2 inner product with exponential weight. And then in this case, we are using H divergence space. So Neumann data becomes essential boundary condition. So the Neumann data is put it in variational formulation with TGP value and penalization. And then other term is divergence term. Is very similar to Stokes equation. We use div up. It's just divergence operator. On the right hand side, it comes from the previous Newton step. And then we can define matrix M and then B. And then after, we can define block matrix A, MB and B transpose 0. So if we have good linear solver like Paradiso or Mampus, if we set the A as sparse solver and some parameters, we could get solution by solving this kind of a linear system. So if that works, so very easy to solve the semiconductor problem by FreeFEM. But unfortunately, double precision arithmetic is not enough. for generate matrix, stiffness matrix, this mass matrix, and the divergence matrix. And also linear solver suffers some numerical errors. So I have to think about the higher quadruple, higher precision arithmetic, and also be careful about the creation of the matrix on the exponential weight for H divergence basis. So what is Rabi-Atomo element? I would like to briefly review here. Rabi-Atomo element has is kind of the vector valued finite element. So here there are three edges of one element K, and the value of Rabi-Atomo element is belongs to the middle of edge. So there are 6 unknowns for one element per one element. And then if we take the divergence of this finite element function, that is become constant on each element. And then also if we restrict on the value on the normal to on the each edge, that is also the P0 element, P0 value. So finite element basis has explicit form, like Phi is sigma times E divided by 2K. K length of K means the area of triangle on X minus P. So we need to evaluate H type L2 norm with exponential weight. So E phi H times phi J times phi I. So there are several ways to evaluate this one. First, maybe I'd like to use most exact one. Is using exact integral equation, integral formula, assuming phi I is found by P1 element. So this is consists of the polynomial of degree 1 on element K. So we can compute this integration by explicitly exponential of the polynomial degree of 1 times degree of 2 polynomial. So we can do the exact integration. The other one, second one, is mostly used in finite element simulation or finite volume. In the finite volume, this is called as Schaffer-Gamel scheme. But this way is we can introduce average of exponential weight on each element. So in this case, there's also the exponential computation could be exact or numeric quadrature approximation. But L2 product of H type space could be kind of the, of course, this is can be exactly or just the lowest order. We can do the numerical integration. The solution could be, in some sense, that is exact, except for taking of the average of exponential weight. The third one is just apply the standard way by FreeFEM. We can use numerical quadrature. So now in the FreeFEM, we can use very higher using a lot of numerical quadrature point, and we can get higher order integration up to degree of 15. So there is a way to do that. So anyway, for this could be done by double operation, but to perform this integration by a quadruple operation, it takes some cost. So first, I will review what what we have to do for exact quadrature. So first, I can introduce so-called n-relative exponential functions, and then this one is kind of the family of the exponential. But to evaluate test function with third order polynomial, lambda 1 squared times lambda 2. Lambda is area coordinate. So this one is consists of the order 3 polynomial in one element with exponential of the polynomial first order polynomial P1 element value. So this can be calculated by explicit way. And then if there is some difference between 3 points, Phi1, P2, Phi3 is a value of each edge vertex. So if phi2 and phi1 is very close to each other, exponential become very close to 1. But problem happens if phi2 close to phi3. The second term, it makes some error. So it's better to use Taylor expansion, or every point are very close to each other. We can do some exponential, Taylor expansion on two variables. But anyway, I can construct this form. And then if I can do this computation by quadruple precision, I am happy to get a good result. But it takes a little bit cost. Of course, it's better way is to do numerical integration. This is a very standard formula of numerical integration. Is we can use omega k weight and then the integration point xk. And then in FreeFEM, this table quadrature, numerical quadrature, the table is calculated by kind of the numerical optimization based on the paper of, on Journal of Computational Mathematics. And then unfortunately, they provide us the good script of the BC command, which can achieve arbitrary accuracy. And so on the original paper, it consists of the table consists of almost double precision plus a little bit higher accuracy. But by starting of such kind of data, we can iterate by continue to Newton iteration. And then finally, I can get very high precision data. It's very simple, just run the code. So now I have prepared this integration point with 74 digits, which cover octuple precision. Is much higher than quadruple precision, but it could be useful in the future. So now I prepared the numerical quadrature rule. So next point is how to do perform the quadruple precision arithmetic. So it's standard way of hardware. There is a definition by IEEE 754. There's exponential part consists of 15 digit, and then mantissa is consists of 112 bit. So it's provide us almost 32 digit accuracy. But this arithmetic is very slow because there is almost no hardware, direct hardware in the world, except for PowerPC, but I have no chance to touch that. So the best solution is to use two-double precision. Is two-double is, we can see 252 digit is present for mantissa. So this is a little bit less accuracy than IEEE definition, but by double, we can use hardware, the floating point hardware. So it's that can achieve faster computation. But of course, it is definitely slower than standard double precision, but it takes about 20 times slower. So that could be sometimes is acceptable, combined with another technique to, for example, using inner iterative refinement or so on. But anyway, now double precision arithmetic is feasible. Just we need to wait a little bit, maybe 5 times or 10 times more time, but we can do numerical simulation by quadruple precision. So this is kind of the opposite to the recent trend. On the recent, many persons would like to know how much faster on the floating float, not the double precision. But in my simulation, I need to use double for good accuracy. Okay, so this is already well-established library. Name is QD. So this QD library consists of the C++ template. So it's easy to use to get the result by double arithmetic. So in my code, what I am doing now in FreeFEM, so I have to prepare numerical integration by quadruple, and also I have to solve a linear system by quadruple. So I need to work with anyway 128-bit data. So an idea is I use a complex data to carry two doubles. For example, the higher double and the lower double is treated as real and imaginary. So, for example, is a complex bracket int array. It can keep this kind of the quadruple number. So also the matrix with the complex type can inherit the same structure of the sparse pattern, but I can keep the quadruple data in complex matrix. In this way, I can keep the data in FreeFEM source code. But unfortunately, I cannot do any arithmetic inside of FreeFEM. So I need to use my own C++ library through dynamic loading library. But anyway, I can compute by this way. Now I have the numerical result. So I wrote my own matrix generator. In here, exp mass q is H divergence L2 norm with exponential weight. And then also linear solver name is dissection, can solve the linear system. And then that can find a kernel of vectors matrix. So now, yes, so almost the mathematical tool is now prepared. Okay, and but I'm a little bit look deeply inside of what I'm doing in the dynamic loading library. So the font script is a little bit small. It is written by C++. So inside, I'd like to generate CRS matrix receiving quadruple data and the return of the entries of sparse matrix. So to do that, I can interface between complex value and quadruple value just by casting, because I use the complex value in FreeFEM as a container for double. And then now in FreeFEM, matrix is stored in hash matrix, so that is accessed by PHM. But here I can extract the CSR format, and after I do my own stiffness mass matrix element mass matrix generator, and then to put all values by CSR format. Of course, in FreeFEM, all the computation is already done by much more sophisticated way, and then we can manage by weak form by script. But in this implementation, I almost do everything by my hand. So I only use half of part of FreeFEM. But fortunately, this code works well. And then also, I wrote this by C++, so the speed is no problem. But of course, I cannot do. Now I only can do very simple computation. Yes, but this is very limitation. So then I need to really merge of two world of the quadruple and the FreeFEM. But today, my result is based on this kind of the technique. So yes. So in the future, what I can do is I would like to summarize. So first version is now is implementing of the FreeFEM by quadruple precision by replacing a real variable by quadruple, just replaced by C++ object. And then almost 80% done. I'm now debugging. For example, sometimes I forgot to define the quadruple value, and then some value become zero, and then, so this I'm now debugging. But in the future, I'd like to do introduce quadruple type for finite element space, also array and the matrix. But to do that, so I need to expand the grammar a little bit, follow the very similar way of the complex. But difficulty is a little bit change of the C++ object. So up to now, I want to do this, but I cannot give the exact future real estate. But I want to. This modification could help to us to get the numerical result for very difficult problems. So the last one is the ingredient is linear solver. So linear solver also have to work with quadruple precision. So name it dissection can solve the sparse matrix that is written by C++ template. So thanks to this template facility, I can use quadruple precision or octuple precision. And then the dissection is using nested dissection ordering, which is obtained by Scotch or Metis. And if one parameter is given as postponed pivot threshold, then almost all part is factorized by following of the dissection nested ordering tree. But after the value which becomes smaller than this kind of threshold, I can postpone the factorization and then gather of the entries on the as the last Schur complement. Then after, so the last Schur complement may be singular if the whole matrix is singular. So dissection can detect of the kernel of such kind of matrix. So real result is I will show the next slide. And then, but this is very kind of a very powerful tool, only based on the LU factorization. But we can understand what is the smallest eigenvalue. Not exactly eigenvalue that matrix has the smallest eigenvalue or not. So we can understand. But for good computation, for good to get better performance, we need to use good plus 3, DGM or DTRSM. On the matrix itself is sparse, but after applying a nested dissection ordering, we can use a dense matrix operation. But unfortunately, there is not yet good standard DGM or DTRSM for quadruple arithmetic. But anyway, now that it works. So this is the result for NPM device problem. There are 4 figures. First 2 figures, top two figures on the left, there's a distribution of electrostatic potential. And as the beginning, I explained, I put the bias on the left side. So bias is 0.38, so very small. It seems small value. So little bit left plateau is higher than right. But after taking off the exponential weight, we can clearly see exponential times 0.38 is almost 40% increase. So this bias is added on the left side. Then I mentioned about PSC. There is exponential weight as diffusion constant. So this kind of the well on the P region, exponential phi is very small. It makes some difficulty for diffusion system. This is bring us so-called floating phenomena. So the system for whole unknowns mathematically is invertible, but in numerically, due to this kind of the diffusion effect coefficient, solution has some kind of the pseudo kernel. So the solution itself is drawn by left bottom, but dissection solver detect pseudo kernel like the light bottom. So this kernel has the ambiguity. So we can put any magnitude of this kernel. It may deteriorate the numerical result. So on the dissection, what it can do is that can detect almost small eigenvalues. So I told you dissection can do computation with the Schur complement factorization. And then at the very last stage, I can compute 6 by 6 matrix. And it contains some suspicious pivot, one suspicious pivot. And then I did inflation of that to compare whether this one is invertible or not. So last one is almost 0, which is understood as a quadruple machine position of the floating machine impression. So by computing QR factorization, there are 6 entries. And the first 4 entry is almost 0.2 or something. And the fifth one is very small, close to the minus 10 to minus 17. The last one is minus 31. The last one comes from the machine impression of the quadruple operation. The second last one, the fifth one, is correspond to the pseudo kernel. So if we treat as this matrix is invertible, the conditional number become almost 10 to the power 17. So it's very difficult to solve. But if I can exclude this value, matrix become moderate. And then, of course, is we need to discuss about this exclusion is better or not. But anyway, the algorithm is like that. So if the Jacobian matrix is supposed to be invertible, the control number is very large, and we have to solve the system with control number with 10 to the power 16. But if we assume the Jacobian matrix is singular, in this case, one-dimensional kernel, pseudo kernel, and in that case, I have to adjust the one component for the kernel vector. But this could be done by another minimization program. And I can do computation with Jacobian and Hessian, and I can manage that. So the last figure shows convergence of the Newton method. So here, this shows the convergence of the against of the residual. So after almost 4 iterations, I can see this has the convergence. And then, unfortunately, this kind of the adjusting is a little bit complicated. Now I only do the double operation arithmetic. So the solution is almost the same accuracy as the double operation. Final solution has almost same as the double accuracy. But if I only do at the beginning with double operation arithmetic, I cannot get this kind of convergence. This is thanks to the quadruple arithmetic. So summary like that. So I can compute the matrix in quadruple operation generation, and also the dissection can do factorization in quadruple operation. The source code is dissection is available inside the FreeFEM repository. So this is my talk, but I need to announce another one. So maybe in 2 minutes. So sorry. Okay. So previous talk is on the kind of the numerical solution on semiconductor, but I'm doing this year another topic with FreeFEM, with a collaboration with industrial partner Denso and RCM. So RCM developed now the GUI interface called as Tanatalk, and then Tanatalk has capability to call set the boundary conditions and then import the geometrical data and then run the script on cloud system. This is developed by Simon and then Frank at RCM, and then now it can kick the computation on the kernel cluster or rescale cluster. And thanks to the Ogawa-san at Denso, with tough negotiation with rescale, FreeFEM 4.7-1 is now implemented, and then we can use this cluster facility with Tanatalk GUI or rescale on GUI. So this is a new announcement of we can use FreeFEM on cluster system. So in real computation, so what I am developing is this is the mathematical detail is already shown last year, but here we have 2 different kinds of boundaries of the 3-dimensional geometry. This is given by step file. So the right side shows the numerical result, but on Tanatalk system, we can import this step file and set boundary conditions by GUI like that. This is inside, there's a step file data, and then we can select the boundary data or initial data. And then after we can run on the cluster system, and we can get the numerical result like that. So this is now is almost done, and then I hope the Tanatalk will be available soon. Thank you for your attention.
Thank you, Atsushi Suzuki. If you have some question, you are welcome. You have 4 minutes to do that. Of course, put on your microphone.
I have a question.
Yes.
So I remember that the dissection sources were put in the FreeFEM repository, I think like 3 years ago.
Yes, it's a little bit old, yes.
Okay, did you make some significant changes that should be put in the repository, or do you think the
Yes,
very-
today's talk is it can work on the 3 years repository,
Okay.
but now I have improvement to mixed precision arithmetic with not only with the quadruple precision, combined with double and quadruple, which part is not yet on the repository,
Okay.
but